Chemical equilibrium. Hello everyone, I'm Dr. Vicky. In this video, I will explain to you what is chemical equilibrium. So what is chemical equilibrium? Before we look at chemical equilibrium, let's first look at equilibrium. Equilibrium is a state in which there are no observable changes as the time goes by. So chemical equilibrium is achieved when the rates of the forward and reverse reactions are equal in a chemical reaction. At the same time, the concentration of the reactants and the products remain constant. In chemistry, we will come across two types of equilibrium, which are physical equilibrium and chemical equilibrium. Equilibrium between two phases of the same substance is called physical equilibrium. It's because the changes that occur are physical processes. The vaporization of water in a closed container at a given temperature is an example of physical equilibrium. As given in the figure, the number of water molecule leaving and the number returning to the liquid phase are equal. The reversible reaction between dinitrogen tetraoxide and nitrogen dioxide molecule is a good example of chemical equilibrium. The progress can be monitored easily because dinitrogen tetraoxide is a colorless gas and nitrogen dioxide is a dark brown color that makes it sometimes visible. Okay, let's look at the experimental data which is obtained for the reaction between dinitrogen tetraoxide and nitrogen dioxide. In this first experiment, referring to the graph, we can see the initial concentration of nitrogen dioxide is 0.2 and dinitrogen tetraoxide is 0. Over the time, when the reaction occurs, we can see that there is an increase in the reactant, which is dinitrogen oxide, and the decrease in the product, nitrogen dioxide. To obtain the equilibrium, the concentration of dinitrogen tetraoxide increase and the nitrogen dioxide is decreased. At one point, the concentration of the both reactant and the product become constant, and the reaction does not stop. By taking the concentration at the equilibrium state, we can calculate the ratio of the concentration. The first ratio, which is nitrogen dioxide divided by dinitrogen oxide, given the value of 0.227. The second ratio, which is nitrogen dioxide with the exponent 2, which is come from the stoichiometric coefficient of nitrogen dioxide divided by the dinitrogen tetraoxide, shows that 4.63 times 10 exponent negative 3. Now, let's look at the experiment result for the initial concentration of nitrogen dioxide as a 0 and dinitrogen tetraoxide is 0.670. Over the time, we can see there's a changes in the concentration of the reactant and the product. We can see that the concentration of the equilibrium for the nitrogen dioxide is 0.0574 and the dinitrogen tetraoxide is 0.643. We can observe that the reaction does not stop, but it becomes constant. When we find the ratio of the concentration at the equilibrium without the stoichiometric coefficient, we found that the value that obtained is different from the previous experiment. However, when we use the stoichiometric coefficient from the nitrogen dioxide, we found that the ratio that we obtained 4.65 times 10 negative 3, which is almost similar to the previous value. When the experiment continued with another pair of concentration of nitrogen dioxide and dinitrogen tetraoxide, we found that it gave a different concentration at the equilibrium. When we calculate the ratio of the concentration without using the stoichiometric coefficient, we found the value that obtained is different from the previous two experiments. And with the coefficient, the ratio remained the same. Hence, from the experiment results, we can find that the ratio of the concentration of nitrogen dioxide, exponent of the stoichiometric coefficient, divided by the concentration of the dinitrogen tetraoxide at the equilibrium gives a nearly constant value regardless the initial concentration presents. So based on the results obtained, we can generalize the phenomenon by this following reaction, which we call as a law of the mass action, where C and D is are the product and A and B are the reactant, and the small letter A, B, C, D are the stoichiometric coefficient. In the law of the mass action, which holds that for a reversible reaction at the equilibrium and a constant temperature, a certain ratio of the reactant and product concentration as a constant value. By looking at the magnitude of the equilibrium constant, one can tell whether an equilibrium reaction favors the product or the reactant. If the K is greater than the 1, then the reaction lies to the right, which is towards the products. Whereas if the K is smaller than 1, we can say that the reaction lies to the left, which is favor to the reactant. So I hope that this video will help you learn about chemical equilibrium. See you in the next topic. Thank you. Bye-bye.